everybody, and welcome to this study session. We will be covering B3 for both SL and HL, and then we'll jump into B4 for those of you who are taking higher level physics. We'll just wait a few minutes, just in case some other students are joining us, and then we'll just get started.
Make sure to introduction. My name is Gordon Hirons, and I look after the physics content on Revision Village. I'll be here in the background on the chat, helping with the Q&A and keeping an eye on the chat.
Thanks for that, Gordon.
Yeah, and then Alejandro here is he's one of the creators for Revision Village. He's an excellent question creator and has a lot of IB physics teaching experience.
Oh, by the way, you might want to have your chat window and the Q&A window opened in case you just want to ask questions during the presentation. Gordon will be handling those questions. Thank you again, Gordon. It means a lot.
And then we will stop occasionally during the presentation so we can answer some maybe more general questions, and Alejandro can actually draw on the screen to explain some things. Yeah, and so we'll have a good session. First half will be SLHL, and then the second half will be HL only, and we will see how it goes. But again, happy to be answering in the Q&A any questions that you do have.
Oh, if you do have a few seconds, maybe you can just write on the chat, just say hi and let us know where you are connecting from. Because I'm sure people from all over the world might be joining us. Hello from Hong Kong, England, India. Hi from Switzerland. So many people. Portugal, Peru.
Oh my gosh.
Spain, Dubai, Germany, Spain, Colombia. Hola, Colombia. London, Singapore, Dubai, Norway, Dubai. Missing some. They're going so fast. Seattle. Good morning from Seattle. Oh, Singapore. Nina Donhau from Singapore. Oh, okay. I'm surely missing many of them. Norway. And Finland. Oh, hi, Finland.
All right, everywhere.
Yeah.
All right, I think we're probably good to go.
Okay, so let's get started. We will start our presentation by stepping into ideal gases. We will briefly describe what is meant by the ideal gas, but for now, the idea is kind of described in the picture that you see on the screen. We think of an ideal gas as a collection of particles that are just moving randomly. This is an idealization of what real gases are. They do not possess all the properties that real gases have, and that allows us to treat them in a more simpler way. Those particles will be moving and colliding among each other, and with the walls of the container, creating a force, a pushing force. Gas wants to expand itself, and if that force is balanced by an external force, the volume might or not remain constant, only if those two forces are balanced. So, particles are constantly colliding with the walls of the container and thus changing their momentum. This is a key characteristic. We will be visiting this concept quite a lot. Particles are changing their momentum, and whenever they change the momentum, a force is created, because a force, as you might know from Newton's laws, is required to change the momentum of a particle. The total changing momentum per unit time, the rate at which the total momentum is changing, is equal to the force exerted by the gas. And that force per unit area is defined as a pressure. And that leads us into one of the first formulas that you will find in the section of your data booklet. Pressure equals force divided area. That's one of the formulas that you will find in your data booklet. Now, definition of what is meant by an ideal gas. Very simple definition. A gas that obeys ideal gas laws at all temperatures and pressure. We will get into what those ideal gas laws are, but for now, we will keep this as a definition. Now, some of the underlying assumptions that are built into this concept, this idea of an ideal gas. Probably the strongest one. We are assuming that an ideal gas is a collection of particles that are experiencing no interparticle, intermolecular forces. They're just moving randomly. Eventually, they will collide with each other. But during the time between collisions, there are no forces between them. That creates a situation in which there's no potential energy, the electrostatic type of potential energy. And the energy is only in the form of kinetic, because due to the motion. Gas particles are point masses. That means that they occupy a negligible volume. The volume occupied by the particles themselves is assumed to be zero. All the collisions are elastic. That means that no energy is lost in the collisions. The total energy remains constant. Particles are moving randomly. There's a random motion of particles within the gas, and the average kinetic energy is proportional to the temperature of the gas. A large number of particles is required for the statistical treatment to be effective. We are assuming that whenever we are describing a gas, there is a large number of particles involved, and the time spent during collisions is negligible. That means it's zero time it takes for particles to collide with each other. Now, moving on. Real gases, on the other hand, they might deviate from this behavior or not, depending on situations. Now, real gases, will say, behave as ideal gases at high temperatures when that situation in which all of the energy is in the form of kinetic, we get closer to that. Particles are moving at high. That is related to a low distance. The average separation between particles is big, so the volume occupied by the particles can be treated as zero. Now, the state of an ideal gas is defined some macroscopical variables like pressure, volume, temperature, and its internal energy. Those magnitudes can, of course, change, and we will be discussing some of the transformations through which ideal gases can go through. First, let's assume that we are changing just the pressure and the temperature, keeping the volume constant. T versus T at constant volume, which is called an isovolumetric transformation. Iso meaning equal, volumetric, well, get the idea, same volume. Now, a higher temperature now means that as the gas increases its temperature, that leads to an increase in, well, let's see, the kinetic energy of the particles is increasing. As the temperature increases, the total energy available for the particles is increased, and the share of energy that each particle gets is increased. That creates an increase in the average speed at which particles are moving. Higher kinetic energy leads to a higher speed. That means that the particles collide with the walls more frequently. Be careful with that one. Do not mention the number of collisions, just the frequency at which collisions are taking place, and at higher speeds. Not only we have a frequency of collisions being increased, the number of collisions per unit time, but also they occur at higher speeds, which creates a rate of change in momentum of the particles being increased. And as we discussed, related to the pressure, and the force, of course, the force exerted on the walls increases, which leads to an increase in pressure. Therefore, for ideal gases, pressure and temperature are positively correlated. They are proportional to each other, and you'll get this type of graphical representation, which is one of the gas laws. Pressure is proportional to the temperature. Let's move
Alejandro,
now, let's consider a situation in which volume and temperature change.
I just want to mention your
yes,
connection is not 100%. It's okay, but it comes and goes. If there's anything you can do on your computer just to tighten things up a little bit, that might be helpful. But we'll keep going and see how it goes.
yeah. Okay, Gordon, I just switched to a different Wi-Fi. Hopefully this one will work better. Thanks again for letting me know. Am I okay now, Gordon?
Yeah, so far so good. I'll say something if it goes again.
Okay, I'll just carry on and then you'll let me know. So, where was I? Transformations between volume and temperature at constant pressure. These are called isobaric transformations. Now situation is slightly different. It starts the same way because we're increasing the temperature. Higher temperature leads to an increase in kinetic energy of the particles, just as before. That leads to an average speed of the particles being higher. Average speed of the particles increases. But now the volume of the gas occupied by the gas increases. We are not letting the pressure to build up. So we should allow the volume to expand, so that the rate of change of momentum of the particles related to the pressure remains constant, which leads to a situation in which, again, the volume is proportional to the temperature. Similar graph, but now with volume and temperature. Lastly, situations in which the transformation takes place at a constant temperature. We're letting the pressure and the volume vary. These are called isothermal transformations, constant temperature. Now, an increasing volume, we're letting that volume increase, leads to an average time between collisions with the wall to increase. Particles would take more time between collisions with the wall just because the volume is higher. It takes a longer amount of time for particles to go from one wall to the opposite wall, or to any wall, because we have high volume, which creates a decreasing frequency of collisions. Collisions will take place less frequently, which leads to a rate of change of momentum of the particles to decrease. You have lower frequency of collisions, the rate at which momentum changes decreases, which leads directly into a decrease in pressure. So this is the only situation in which you have an inverse proportionality between pressure and volume. As the volume increases, pressure goes down, decreases in a proportional way. Now, all of this magnitudes, pressure, volume, and temperature, and also one dedicated for the amount, the quantity, the number of particles that we have, can be summarized into this ideal gas equation. This is, once again, one of the equations that you will find in your data booklet. And let's go quickly through what each of those symbols represent. For P, we have pressure, of course, pressure measured in pascals. V is for the volume, typically measured in cubic meters, but some other units might be used. Little n, the little n goes for the number of moles of gas. R is a constant, known as a gas constant, and this value can be found within the first pages of your data booklet. T is for the temperature, absolute temperature, always in Kelvin. Big N for the number of particles. You might be using this equation given a certain number of moles, or alternatively, you might be given the number or asked for the number of particles of the gas. In that case, big N will be used, representing the number of particles. And once again, we have a different constant, KB, representing Boltzmann's constant, which its value can be found, once again, within the first pages of your formula booklet. Now, one thing to notice is that we have an equality involving nRT equals nkBT, which leads to mathematical consequence of this is that having the number of moles multiplied by this constant R equals the number of particles times Boltzmann's constant. This equation, this equality can be rearranged as follows. And the ratio on the right-hand side of this equality, the number of particles, the number divided by the number of moles, is in itself another constant. It's called Avogadro's number, represented by Na. And this final equation can be rearranged into this one, which is one of the equations that you will find within your formula booklet. Now, these are the constants that are present within these equations. You will find them right next to each other, as you see on the screen right now. in your formula booklet. Let's move on now. Now, for ideal gases, we still need to explore a few expressions that are related to speed of the particles and energy of the particles. So let's start by saying that the change in momentum of particles due to collisions with a given surface gives rise to pressure in gases, as we discussed earlier. Now, pressure is related to the average translational speed of molecules as given by, now, this one is a new formula within the syllabus of the IB. If you've been practicing with past papers, you have likely never used this formula. Makes its new appearance this year. So do keep in mind that whatever practice you did with past papers, you likely never have used this equation. It's one of the equations that you will find in your data booklet. The symbols that are present in here are, well, P for pressure. You have this Greek letter rho. For those of you who joined us in our previous study session for electricity, this letter was used for a completely different magnitude, which was resistivity. Same letter, different meaning. It's representing gas density, the density of the gas, the mass per unit volume. And V represents the average speed of the particles measured in meters seconds minus 1. Now, the internal energy represented by U of an ideal monatomic gas, you will only be dealing with monatomic gases, is given by, well, you have two alternative expressions, similar to how the ideal gas equation was written, once in terms of the number of moles and once in terms of the number of particles, 3/2 and RT. Again, one of the equations that you will find. Now, there's an alternative expression that can be obtained by just realizing that nRT or nkBT can be substituted using the ideal gas law, but just PV. Same expression for the internal energy of an ideal gas, just that's written in terms of the pressure and volume. This one's not part of your formula booklet. It's just a combination of two equations that we described previously. Now, if we take the internal energy of the gas, this expression, and we just divide the expression by the number of particles. That means U divided N being the total number of particles. Well, mathematically, we get this expression 3/2 kBT, which has a meaning, right? Because if we take the total internal energy of the gas and we divide it by the number of particles, the number that we get is representing the amount of energy that each particle has, which is 3/2 kBT. That energy of this particle, it's in the kinetic form. So this equality arises like 1/2 mass V squared, kinetic energy of a particle, where M is just the mass of one particle, equals 3/2 kBT. This is not an expression that you will find within your data booklet, but you're likely to use it in case a question related to temperature and speed is asked. Now, might be important to notice that this is the first expression that we have combining speed and temperature. And you might notice that temperature is not proportional to the speed, but to the square of the speed. Makes a lot of sense because temperature is proportional to kinetic energy, which is proportional to the square of the speed. I thought it was interesting to mention that the formulas can be combined to obtain new formulas like this one. Okay, as far as theory concerns, we are done. Let's now be headed into one of the first problems that we will be discussing. Okay, this is a multiple choice question. So I'll just be quiet for just a few seconds for you to do your reading, maybe decide which is correct option, and then we'll discuss it. Okay, hopefully you've located what the correct answer was. Let's go quickly through this problem. Question is, under what conditions of density and pressure does the following graph represent how the volume of a real gas varies with temperature at constant pressure? Now, a few comments before diving in. Notice that the temperature that's being represented in the horizontal axis is represented in degrees Celsius, which means that we would have 0 degrees in here. So we have this negative temperature region, which only makes sense when we're treating temperature in degrees Celsius, not in Kelvin. That x-intercept that you see right there would represent the absolute 0, right? When we're 0 Kelvin located, or negative 273. So, question, how the volume of a real gas varies with temperature at constant pressure? What conditions? What is the situation? What in terms of the pressure and density? What we definitely need a low pressure. We need particles to be as apart from each other as possible. So we can cross out options C and D. So we should only decide how the density should be. And well, low pressure particles as far apart from each other as possible. Low density is what we need, which makes correct option A. And hopefully that's what you thought as well. We have a few more problems to discuss. So we'll do the same thing, okay? Share the problem with you. Be quiet for a few seconds, and then we'll discuss it. Okay, so let's see. Problem goes like this. An ideal gas is held in a container of volume V and at a pressure P. Gas is pumped into the container so that the number of molecules doubles. Okay. Sorry. Number of molecules doubles, and heat is added so that the average kinetic energy of the gas also doubles. Okay. Kinetic energy being doubled, that means that the temperature is doubled. The volume is adjusted so that pressure remains constant. Question is, what is the new volume of the container? Okay. Even if you have or haven't realized what the answer is, we might just as well describe a procedure, I'll call it that way, that will allow you to solve this type of questions, and not only when gases are involved, but in any situation. We have the situation that's being described is the one in which some magnitudes are constant, some others are doubled, or changes are introduced. And that is described by this equation. And it is sometimes helpful to identify which are the magnitudes that are kept constant and try to work yourself mathematically to send them over to one side of the equation and to keep the ones that are changing on the other side. In this situation, we are asked for the new volume, so volume is definitely changing. The number of particles is doubled, so N is doubled, and the temperature is also doubled. So we can rewrite this equation with all the variables on one side and all the constants on the other side. In this case, it would be P divided R, both constants, which means that the expression NT over V must also be constant, given that the pressure is constant and R is itself a constant. The right-hand side of the equation must also remain constant. So what's going on with the number of particles? The number of particles N is doubled, so this is multiplied by 2. And the same with the temperature. We're told that the kinetic energy is doubled, so temperature is also multiplied by 2. So the real question would be, how should the volume change for this magnitude to remain constant? We have a times 4 on the numerator. We should have the same thing in here. So volume should be multiplied by 4, and this is hopefully what you thought the correct answer was, B. 4 times B. No, there's no way of using any numbers. All the expressions, all the magnitudes are just being described as symbols, letters, P, B, and I find this to be an extremely helpful way of dealing with this type of questions which are very popular within the AB. Okay, a few more questions to go. Let's do another one. Okay, let's see what we've got. An ideal gas is enclosed in a syringe. The gas has a volume of 20 milliliters, a temperature of 20 degrees Celsius, and a pressure of 10 kilopascals. The syringe is heated to 40 degrees and the volume of the gas is reduced to 5 milliliters. Question is, what is the new pressure? Okay, let's start by realizing that pressure, volume, temperature are changing. So whatever initial pressure and volume divided by the temperature we have in the initial situation will be the same as the pressure in the final state times the volume in the final state divided by the temperature in the final state. P times V divided T remains constant, so whatever value we got initially will be the same value as we got at the end. So what is the question? Question is, what is the new pressure? This is what we are trying to find. So some teachers or student might be interested in just substituting some numbers right away and then working yourself out of this equation, dealing with the numbers. I myself like to solve the equation with the symbols, and I encourage you to do the same thing, just solving symbolically, and only then will substitute the magnitudes. As an examiner myself, let me give you a hint of why this might be helpful for you. Now, we all make mistakes, at least I know I do. And when the numbers are plugged in right from the beginning and a mistake happens or something goes wrong, it's not always possible for the examiner, even if we try to do our best, to realize what's going on because of all the mixture of numbers. Whereas if you just work with the magnitudes and the symbols, the examiner will be able to tell, okay, the intentions were good, the equation is correct, the algebra looks okay, maybe there was a mathematical mistake, maybe due to a calculator mistake or something. It's convenient to try to move the usage of the calculator as forward as possible within the problem, but that's maybe you're used to doing things differently, and which is perfectly fine. So let's solve for P2. We'll get P1 times V1 times temperature 2 divided temperature 1 multiplied by V2. Let's just put some numbers in now. Initial pressure, we have 10 kilopascals. That kilo might be written as 10 to the power of 3, but I already spotted out that all the options are given to us in kilopascals, so I'm keeping that kilopascals and not expressing it into its 10 to the power of 3 form. Now, initial volume, initial volume 20 milliliters, which is not the typical unit that you will see, but we also have the volume expressed in milliliters or the final state. So those milliliters will get simplified. Now, temperature, final temperature. Be careful not to use that degrees. You need to add 273 so as to write each temperature as an absolute temperature. For 40 degrees, we have 313 Kelvin divided by the initial temperature. It was 20 degrees Celsius, which corresponds to 293 Kelvin. And the final volume, where is it? 5 milliliters. Okay, do the calculation. Maybe you can check right now with your calculator to get the same results I do. It's 42.7 kilopascals. That's a value that's a calculator value, which rounds to two significant figures as 43, which makes D the correct option. And well, hopefully that's what you've got from the beginning. Still a few more problems to go. That will allow us to discuss some of the magnetism and formulas and concepts that were presented at the beginning of this presentation. Let's move forward. Okay, let's see. This might be a tricky problem, some of you, especially because we have some liquid water over there. Well, okay, let's read. An ideal gas piston of total volume 900 cubic centimeters contains 600 cubic centimeters of air. I'll just write air in here. And 300 cubic centimeters of water. At a temperature of 27 degrees Celsius. The system is cooled and the piston contracts at constant pressure. Okay, pressure remains constant. What is the approximate total piston volume at the point where the water first starts to freeze? Okay, big question. What is the point where water first starts to freeze? Okay, you should know that that happens at 0 degrees Celsius, which corresponds to 273 Kelvin. Otherwise, there's no way out of this problem. You need to know that. Okay, so you have a constant pressure through this transformation. So we can use the same expression as before, but just forget about the pressure. Instead of P times V divided T, no pressure, which is right, V divided T. Okay, so whatever volume was occupied divided by the temperature in the initial state will correspond to the volume, the final state, divided by the temperature. And we ask for the volume and the final state. So let's solve this equation for V2. Just be V1 multiplied by T2 and divided by T1. Okay, let's just plug some numbers into this equation. Now, for V1, what volume should we use? Should we use the total volume? Should we use the volume of air? Well, we are dealing with an equation of gases. That's why we are here today, to discuss gases and ideal gases and how they behave. So that volume occupied by the water is not going to be used. The volume occupied by water is not going to change, at least not significantly. We assume that's not changing. So the initial volume will be 600, only air, only the gaseous part. So 600, once again, when using this equalities, you don't need to make any unit adjustments. However, when you use the ideal gas law, PV equals nRT, given that you are using a constant R or kb, you do need to use the corresponding units like cubic meters and moles and pascals, but that's not our case now. We can keep that 600, those 600 cubic centimeters. Not the Celsius part. The Celsius needs to be converted into Kelvin. And temperature in the final state will be the one in which water starts to freeze, 0 degrees or 273 Kelvin. Divided by the initial temperature, which was 27 degrees, which converted into Kelvin would be 300 Kelvin. Okay, let's solve V2 for now. The V2 value. Okay, do the calculation. You can check right now if you have a calculator next to you. That'll give you, okay, you can simplify those kelvins, units, sorry. There we go. You will get 546 cubic centimeters. Mm. Now, a very, very powerful piece of advice now, because this might happen a lot of times. You might get a number when solving a multiple choice question, and you see the number that you have just obtained as listed as one of the options. We all get excited. Hey, it's there. That should be the answer. That's the moment in which you should like go slow and make sure you are answering the question. Let's reread the question. The question was, what is the approximate, where is it? What is the approximate total piston volume? You're missing that total word, you're missing this problem, and you get 0 points because you're missing out. The answer will not be 546. 546 cubic centimeters would represent the volume occupied by the gas, the volume occupied by the air. But the piston will still hold those 300 cubic centimeters of water. Now, it's a tricky thing to do to students, but it's the way it's going to be. So yeah, you might have realized that we still need to add those 300 cubic centimeters of water, leading us into a 846 cubic centimeters for the total volume. Okay, and that's it. Okay, I got one more problem to go, and then we'll go straight into the Q&A, and we'll discuss whatever questions might still be floating around. So, final problem. Okay, this is, I find it to be a really tricky problem. Maybe you think the same. The situation is given to us in a way that might not be easy for you to even realize what the final state will be, what variables are there to be defined in its final state. I'll do the reading and then we'll describe what's going on. So a 10-liter cylinder containing nitrogen gas, guessing this one, nitrogen gas, at a pressure of 20 megapascals is used to fill, oh, the other one, a 20-liter cylinder that initially contains nitrogen gas, same nitrogen, at a pressure of 2 megapascals, okay? We have one cylinder at a high pressure, the other one at a lower pressure, different volumes. Question is, what is the final pressure inside the two cylinders? Okay, let's try to understand what's going on. We have high pressure on the smaller cylinder, 10 times the pressure of the bigger cylinder. So as the valve is opened, some of the gas will be allowed to pass from one cylinder into the other one until as a point in which that motion will no longer take place. The system will be in equilibrium. Now, we do not know what that pressure is going to be. We might guess somewhere in between 20 and 2, given that the pressure of one of the cylinders is 20, the other one is 2, so they might end up at somewhere in between pressure. So you, by just realizing that, you might be able to spot out that this one makes no sense, right? 22 pressures are not added. They will both end up at an intermediate pressure, but it's not going to be the mean pressure or the average pressure. Now, it's a trickier problem, of course. Tricky problem. Okay, so here's what we need to understand. Whatever number of particles or number of moles we have on one cylinder, and whatever number of moles we have on the second cylinder, those particles will still be there. So we will end up having a total, a gas with a total number of particles that will just be the sum of the particles that were present in one cylinder or the other cylinder. So somehow we must add those particles. That's where we will be headed first. So let's start by just writing the gas law equation. I'm writing it in the nRT form. You can also, it will give us the same result if you go with the big N and the KBT, the other version of this law. I'm just using this one. It's the first one that you will find. So let's solve this equation for N, the number of moles, which we know will be added in the final state. Okay, so we'll get a number of moles from the first cylinder. I'll just call it N1, which will be the pressure in the first cylinder times the volume in the first cylinder divided by gas constant multiplied by a temperature. Now, I'm not writing T1. You might, of course, write T1, but since they are at the same temperature, we don't need to go into like T1 and T2 thing because just not realistic. We have the same temperature, so I'm just going to use T for both cylinders. Same expression for the number of moles of gas present in the second cylinder. P2, I know it's 2 megapascals. I'm not using that value, not until the very end. P2 times V of the second cylinder divided by R, and the same temperature represented by T. Okay, when those two gases are mixed, these two quantities are added. So we will end up having a final number of particles, sorry, final number of moles, which will just be the sum of those two expressions. They have a common denominator, R times T. So we must just add them this way. The total number of moles will be P1 times B1 plus P2 times V2. And that's it. Now, Now, in the final state of the system, which will have a total volume, you might have guessed that already, the total volume which we will have to use is the sum of these two volumes. The total volume occupied by the gas will be 30 liters. The volume, of course, is added. We can now use this expression into the gas law. So let's go. So whatever final pressure we get multiplied by the final volume, I'm just writing it as BF. We know it's going to be 30. I'm just leaving the symbol, equals final number of moles multiplied by RT. And all that we need to do is to substitute the final number of moles in here, which, by the way, you might be able to realize that that RT will be simplified from the expression, and we'll just get B1 times B1 plus B2 times B2. And those R and T's are canceled. All we need to do now is to solve this expression for the final pressure. This problem was, of course, much harder than the all previous problems that we did. So we'll get P1 multiplied B1 plus B2 multiplied B2 divided by the final volume, which will be 30. Let's just now put some numbers into the expression. Pressure of the first cylinder, 20 megapascals. Volume of the first cylinder, 10 liters. Pressure of the second cylinder, 2 megapascals. And volume of the second cylinder, 20 liters. All of that divided by the total volume occupied by the system, which will be 30. The only two magnitudes that were added are the total volume and the volumes and the number of particles. Okay, that's it. All that remains is to perform this calculation. That calculation will lead you into 8 megapascals. That is the answer to this question. And that's it. So now it's time to see if there are any questions that are still unanswered. Meanwhile, the QR code that you see on the screen will give you access to a Google form, which you will be able to give us some feedback, and we will highly appreciate if you can take a few seconds, scan that QR code, and go straight into the feedback form. It will be really helpful for us. It is helpful for whatever future study sessions we might offer. Gordon, how are we doing in terms of questions and answers? Are there any questions that?
Incredibly busy on the Q&A. Incredibly.
Thank you
So
very much.
managed to keep up for most of it. 42 answers given, so I'm pretty proud of that. There was some questions about where I kind of lost track of where the questions came in and what you were talking about because I was so busy answering the other questions. But if we start with the very most recent ones about the most recent question, like from Mateo is asking, why did R and T cancel out on this one that you just did?
Okay. Yeah.
Yeah. I'm going to keep working on some of these.
Okay. Let me clean this up just a little bit, and I'll show you, Mateo. Okay, I'll use a different color now for you just realize what the difference will be. Okay, when substituting their expression for the final number of moles, we will get P1. We will get a fraction, right? P1 multiplied B1 plus the expression above. I'm just writing the expression above, no thinking in here, just copying and writing, divided by RT. That is NF, that is the total number of moles, and that is multiplied by RT. That's why RT gets canceled because of this. So just multiplying and dividing by RT. And hopefully that's clear. If anyone just was anxious to substitute some values, you might not have realized that the value of t, well, you didn't even have the value of t. Now that I see, yeah, it didn't even have, so you could not have substitute any t value. Yeah, it wasn't given to you. Okay, hopefully Mateo was clear. Gordon?
Yeah, sorry, I'm just trying to
Yeah,
keep
okay.
up. I would couple of other, so we can get through a couple of questions on here just verbally, and I'll try and figure out the rest of them. There was someone whose name I don't want to mispronounce too badly, but it's I believe Zirkonu. We'll try and get back to what question you're asking about. Okay, Jaidev is asking why do we use PV NRT instead of just P1 V1 over T1 for this specific question? One of the keys to this is we need the number of particles in each container, and we need to keep track of those moles and add them together. So that's quite important, although you can see it does all end up canceling out in the end.
That PV over T equal is a constant, can only be used when it's like one single gas with the same number of particles that is being transformed. And here we have a mixture of two gases. The total number of particles is changing. Yeah, you need to work with the complete gas equation in here.
What about Noah's question that just popped up, Alejandro? Do you want to answer that one?
Oh, sorry. I need to switch screens. Just give me a second. I still cannot see the questions. Oh, sorry. I'm sorry about this. I cannot see them right now.
Okay, sorry, he's asking, could you do for this question PV over T and then just add them and that make that equal to V final, P final? It does work. It does simplify out to that, doesn't it? You can see that it simplifies out to
Ah, yes.
P final, V final equals P1 V1 plus P2 V2, which someone actually previously asked in the Q&A and I dismissed it and then came
Ah,
back and apologized. So, so that is effectively what has been done, Noah, I think.
yeah, I can think of a physical reason rather than just a mathematical consequence of that being equal. I understand that what they're claiming is that we can just take P1 writing on the left side of the screen. Like if you take P1, B1 plus C1, and then you add whatever pressure and volume and temperature, you will get like, is that what they are saying, Gordon? Think so.
I believe so, yeah.
Yeah, I've never seen this. I know I can see that mathematically it works. It's just that um, I wouldn't bet that this works in every conceivable situation. We do know that the gas equation is a law, and
Yeah.
um, probably because the temperature remains constant, so the denominators are
Yeah.
being cancelled. But I cannot think of how this would work. No, I wouldn't recommend going this direction, although it might seem mathematically the same. Otherwise I've never seen that type of work.
I think, I'm really apologetic to all the people who have the questions on here, and I'm going to keep um, trying to answer things in the Q&A, but I think we need to move on to the HL part of the session.
Ah, yeah, because of time. Yeah, we have some
Yeah,
time restrictions.
okay.
Yeah.
So SL students, if you have questions pending in the Q&A, I'm going to do my best to run through those, okay? Uh, we're moving on to higher level material though. So if you're SL and leaving us, we would really appreciate the feedback. Also, SL, if you want to come back in 35 minutes when we're finished the HL, then we sort of open up for outright general questions. Someone asked on the Q&A, what advice does Alejandro have sort of as a teacher and examiner of just overall exam prep? And that kind of question we answer at the
At the
end of
end.
90 minutes.
Yeah.
Okay, so if you want to pop back in half an hour, that's fine as well. Okay, but otherwise we
Okay,
can
let's
go on to
let's
the
do that, Gordon. Let's step now into the HL territory, and then at the end we'll answer questions related to HL, SL, or whatever general questions about physics you might still have. Okay, so let's move on. Now, stepping into B4 section of the syllabus. Now, first law of thermodynamics, that's where we are headed right now, which results from the application of conservation of energy to closed systems. It's a consequence of conservation of energy. It requires its symbolical representation by means of this equation. Q equals delta U plus W, one of the equations that you will find in your data booklet. And let's see what each of those symbols represent. Q is representing heat. All of these magnitudes are to be expressed in joules, and they somehow represent a form of energy. In the case of Q, thermal energy or heat. Delta U, the change in internal energy of the system, and that W goes for the work done by the system. Now, there's a very tricky aspect to the usage of this equation. It turns out that each of those quantities, Q, delta U, and W, can be positive and negative, and you need to be aware in which case each of those is positive or negative. So I'll run you quickly through each possible situation. This is called the sign convention that we are using. So let's start with Q, heat. It will be positive when heat flows into the system. Positive, heat is going in. And negative when heat flows out of the system, when thermal energy is extracted from the system. I might be using different words, but one is for in, heat going in, the other one is for heat flowing out. Now, as for delta U, the internal energy, this one might be easier. Delta U being positive just means that internal energy increases, going up, and delta U negative means internal energy decreases. I bet that this is an easier one. Now for W, we have positive value of work. This might be the trickier one, I think. Work is done by the system. The system that's doing work on the surroundings, on the environment, on the outside. If it's too confusing, it's a personal thing. I find it easier to remember that on a thermal engine, the typical steam engine situation, you put heat in and you expect work to be done. And that situation is when both W and Q are positive. Heat going in, work being done by the system. It's easier for me to remember just those two, and then I try to, because my memory is not as good. Well, it was never good, and now it has gotten worse. But you do your best. You do need to remember the meaning of each of the symbols. And okay, lastly, when work is negative, W is negative when work is done on the system by an external agent that's doing work on the system. Now, we are describing gases, basically. The system will be formed by a gas, which for the gas to do work, it needs to expand. And that expansion leads to an increase in volume. And this work will be related to that increase in volume by this equation. Work equals pressure times the change in volume. This is another equation that you will find in B4. Now, the relation between work and delta V, the change in volume, is a close relationship, of course, because if delta V is positive, that means that W must also be positive, which means that during an expansion, an increase in volume, the work done by the system is positive, which hopefully makes a lot of sense. An expansion means that it's the gas that's pushing against the walls of the container, creating more volume for itself. That pushing demands a positive amount of work, so they are highly related. An expansion is always related to a positive amount of work. And the opposite, for a compression, change in volume is negative, so negative amount of work. Negative amount of work done by the system because someone else is doing work on the system. Now, variation change in the internal energy of the system. It's related to the change in temperature, extremely similar equation than the one you will find in the SL section, but now with the deltas. Delta U equals 3/2 NR delta T. which establishes a relationship between the signs of the change of the variation in internal energy and the delta T, the change in temperature. The internal energy increases if the temperature increases. Of course, they are related to each other. Temperature increases, we have positive value of delta U. A similar thing when temperature decreases. So the idea is to keep track of delta T being connected to delta U and delta V being connected to the amount of work that's being done. Hopefully, I will not be creating any more confusions that you might already have. So let's step now into this territory. We have a PV diagrams, diagrams in which the variables, the magnitudes, the macroscopical variables of a gas can be represented, typically pressure in the vertical axis and volume in the horizontal axis. And we have a single point in there represented by the letter A at a given volume and a given pressure. So a single data point, this is how it all starts. A single data point in a PV diagram defines the volume and pressure of a gas. Of course, we have an X coordinate and volume and a Y coordinate for gas. You could ask yourself, what is the volume that the gas occupies? Of course, it's to be careful with this part. Do not just keep that 2. Don't forget it's 2 times 10 to the negative 3. Many students would tend to forget this and they lose a lot of points because they're not reading out what the scale on any given diagram is. So the volume would be 2 times 10 to the power of negative 3 cubic meters, and the pressure would be 15 times 10 to the power of 5 pascals. That's it. Now, according to the equation of an ideal gas, we do know that PV equals nRT or nkBT, which means that if we are given information about the number of moles or the number of particles that the gas has, the temperature of the gas at that point can be calculated. Okay, we can extract, even though this diagram has no direct information about the temperature, well, we can calculate it as long as we're given information about the number of particles of the gas. We can just use the ideal gas equation to find what the temperature at that particular point would be. Of course, if we are given information about the number of particles or number of moles. Now, this goes for a single point. Now, as a gas undergoes a transformation, that point will be moved into a different location because the gas might have a different volume, a different pressure, a different temperature. Things might change. And that's where we are headed right now, into discussing the isovolumetric transformations. No specific order. Now we are about to describe 4 different transformations. You might already know their names. This one, I don't know, might be the simpler one, maybe. We'll see. Okay, we have a situation involving a transformation of a gas that starts at A and goes down into B. Now, there's no particular reasons why I have chosen this graph to move downwards. Just I needed to choose one of them, and I chose this one. So pressure is going down, okay? So things that we need to understand about any isovolumetric transformation, in particular this one in which the pressure is going down. So along the transformation AB, volume remains constant, of course, though that segment is created upon an infinite number of points, and they all share the same volume. They all share the X coordinate or the horizontal coordinate. Delta V is 0. There's no change in volume. That's what an isovolumetric transformation is, transformation in which the volume is no changing. But since the volume is not changing, now that we have introduced the first law of thermodynamics, we can tell that there's no work being done. W will be 0, being delta V connected to the work being done. We know that the pressure decreases, it's going down. The opposite would happen if the transformation occurred going up. But in this case, pressure is going down. And we might ask ourselves, how can the pressure decrease if the volume remains constant? That's a fair enough question. Like, how could the pressure decrease if the volume remains constant? Well, some other magnitude should also be changing. And that one is the temperature, right? For the pressure to decrease, for the particles to exert a smaller amount of force on the walls of the containers, those particles should be hitting the walls of the containers less frequently, which means particles should be moving at a slower speed, which leads to, of course, a decrease in the temperature. So temperature is dropping in this transformation. Delta T is negative. And let's take it one step further. If temperature is decreasing, and you remember that temperature was related to another magnitude, it was related to, of course, the variation in internal energy. So even though we cannot like spot out what the internal energy of the gas, by just looking at it, we know that the internal energy of the gas must be decreasing. Delta U must be negative. And is there anything we can say about heat? Is heat flowing into the system? Is heat being extracted from the system? Let me take a few seconds to think. We have a negative delta U and no work, which leads to a situation through the first law of thermodynamics. Of course, we have delta U, there we go. This one is negative, this one is 0. We have negative plus 0, so Q is negative. It's a mathematical implication of the first law of thermodynamics, which means that heat is being extracted from the system. All of that can be understood, described by just looking at the graph. So let's take this into a problem-solving territory kind of thing, involving an isovolumetric transformation. So I'll just go with it, okay? A 0.50 mole sample of an ideal gas is kept inside a container with a volume of 2 × 10⁻³ cubic meters. That's the volume. And it's not going to change. We are describing an isovolumetric transformation. The pressure of the gas, which is initially 15, like in the graph, 15 × 10⁵ pascals, is reduced to 5 × 10⁵ pascals. So this problem corresponds to the transformation that you see described graphically. Calculate the amount of heat that was removed from the system. Okay, let's start. We can first express the temperatures of the gas at A and at B. We can calculate those two temperatures. We can calculate and express them, okay, by using the gas law. The temperature at A will be pressure times the volume. Now you notice that I haven't used BA in here just because there's a single volume, same volume for B and A. You can, of course, write it as BA divided NR. Now, if you just substitute the values, it will lead you into this temperature. We don't really need it because as I'll show you, things will somehow sort themselves out. But if you're just willing to substitute the numbers, this is what you'll get, the temperature at A. Similarly, the temperature at B can be calculated. You'll, of course, get a smaller value, though you don't need to, but this is what you will get. Now we can calculate the variation in internal energy. We know how to express both temperatures, and we might also know what the temperatures are. So we know what the delta T is going to be. So delta U equals 3/2, that's the formula, NR delta T by delta T, which means final minus initial, always final minus initial. TB minus TA, you can substitute the numbers in here, or just aside it, just substitute the expressions, okay? Whatever works best for you. I've taken this symbolical path of substituting the expressions. We have NR, NR, they will all get simplified from the expression. And this is what we end up having, PV times V, which has a common factor B that can be extracted, and we'll get this expression, pressure at B minus pressure at A, which will be negative. Of course, the pressure at B being smaller than the pressure at A, this will lead us into a negative delta P would be the variation in pressure, negative variation in pressure. Okay, if you follow along calculation, that's what you'll get, negative 3,000 joules. That's the variation in internal energy. But given that there's no work being done, that variation of internal energy corresponds to the heat, Q. Negative 3,000 joules, which means that 3,000 joules of thermal energy were extracted from the system. And hopefully this first example is clear enough for you. because we're moving on to the next type of transformation. This one, isovolumetric, and identify them as a vertical segment, a vertical line on a PV diagram. Let's move into the next one, isobaric expansion. Okay. Okay, situation has now changed. We still have an initial situation represented by A. Now I have chosen to move rightwards, no particular reason. That's why it's called an expansion. It's going rightwards. Volume is increasing from A to B at a constant pressure. So along the transformation AB, let's describe what's going on in here. We have a pressure that remains constant. Okay, volume is now changing, pressure is not. Delta V is positive. We are increasing the volume because me just choosing to have this arrow pointing rightwards, this means that the volume is increasing. It's an expansion. Given that the volume is increasing, the amount of work W is positive. They are closely related, delta V and W. Okay, so with delta V and W both being positive, what's going on with the temperature? Is there a way we can realize if the temperature is going up or down? Not by looking at the axis, you need to think of what's going on with the gas in here. So let's see. We have a volume that's increasing. That means that particles would need to travel longer distances before they can collide with the walls of the container because of having a larger volume, but the pressure somehow remains constant. That means that even with need of to travel longer distances, particles are still able to collide with the walls of the container at the same rate. That means that particles should be moving faster, which means that the temperature increases. Delta T is positive. Particles should be moving faster so that the pressure remains constant. And do you remember what delta T was connected to? The change in temperature, variation with temperature, was related to the internal energy, whatever's going on with the temperature. Same thing happens in terms of signs with the internal energy. Delta U becomes positive. So it's increasing its internal energy. So from the first law of thermodynamics, we have a positive delta U, positive W, so Q must be positive, which means that heat is inserted into the system. Heat is flowing into the system. An external something is allowing heat to go inside. Now let's just do what we did before. Let's just solve a simple example that corresponds to this graph to see how things might be dealt with in terms of the equations. So problem, 0.50 mole sample of an ideal gas, same as before, undergoes an expansion at a constant pressure of 15 times 10 to the power 5 pascals. The volume increases from 2 times 10 to the negative 3 to a final volume of 5 times 10 to the negative 3 cubic meters. Calculate the amount of heat that was inserted into the system. Okay, there's no direct approach. We need to deal with different magnitudes first. We cannot just start from scratch and just expect to do this to lead us into a calculation of Q. We need to take things slowly. We can first calculate the amount of work done by the gas. We have a dedicated expression for this, which is W equals P multiplied delta V. Pressure is given to us. You can extract it from the graph, 15 times 10 to the power 5 pascals, and delta V. I'm just writing delta V as a difference between the volume at B and the volume at A. It's positive, of course, because the volume is increasing. Just multiply these values. That'll give you 4,500 joules. That's the work done by the gas. Now, it's interesting to notice that we are multiplying two magnitudes, which correspond to an area. Geometrically, the product we just did, multiplication we have just performed, corresponds to the area of this rectangle. This value represents the area of the graph. Okay, work will always be interpreted as the area under the graph, which in this case is a rectangular area, so we can just calculate it. With a minor distinction that, well, the area has a positive magnitude, but work can either be positive or negative depending on which direction the gas is being transformed. In this case, work is positive, the area will always be positive, so work is the same as the area. But if the situation is reversed from B to A, of course, we will have the same area, but the work would be negative 4,500, which is not this case. So I'll leave that for another time. Now we can calculate the variation in internal energy. We need to find the variation in temperature to do that. Okay, we need to find that variation in temperature. And this is similar to what we did before. So I'm speeding things up just a little bit. We would have to find what the temperature of the gas at B is. We would also need to find what the temperature of the gas at A is. I'm just copying the same expression from before, with the only difference that now the pressure is the one that gets no specific name, which is have one pressure, and the volume is the volume of B and the volume of A. Once again, mathematically, those N times R are simplified from the expression, and we get this: 3/2 of pressure times the variation in volume. Okay, this calculation, that would be the variation in internal energy. So you have work and variation in internal energy. That will allow us to calculate the amount of work by just adding those two magnitudes. Sorry, the amount of heat by just adding those two magnitudes. Delta U plus W. Positive means thermal energy was added into the system just as we predicted by just analyzing the shape of the graph. Still have two more transformations to go. There's a lot of theory to cover, so I'm stepping forward. Now, isothermals. Let's first describe what isothermals are, how to spot them out, and then we go into an isothermal transformation. So very simple definition, okay? Transformations in which the temperature remains constant. Kind of an obvious definition. Isothermal. Iso meaning equal, thermal, same temperature. Along an isothermal curve, P times V remains constant. Okay, so along any isothermal transformation from whatever initial state A, the system evolves into a final state B, P times V will remain constant. That creates a situation in which the transformation follows a curved path. You can see several isothermals represented in here. For that particular one between A and B, which is in red, each of the points along this curve would represent a point in which the gas has the same temperature. Of course, volume is increasing, gas temperature decreasing in an inversely proportional way, as we presented, as we discussed at the beginning of this presentation. But we have different isothermals in here. Okay. Now, since it is a product, pressure times volume, that remains constant. And once again, although in a different scenario, the product it always represents some type of area. And this is not the only place to find an interpretation of areas throughout the syllabus. There are many places in which the area has a special meaning. In here, that area under those two rectangles, the area associated with those rectangles that has one of its vertices at the graph, they are of course equal. For A, you can spot right by just looking at the numbers. You have 2 and 15, which is 30, and for B you have 6 and 5, which is also 30. Those two rectangles will always have equal areas. Now, let's now consider two different isothermals on this graph. You can see the red curve, an isothermal that connects A and B, and this blue one that connects C and D, different temperatures. Now, the temperature at A would be the same as the temperature at B, being both on the same isothermal, and the same for C and D. Question would be, which of those temperatures is higher? And which one's lower? Okay. Might be easy, I know, to realize, well, depending on where you want to go. Maybe you can think of how to get into a conclusion about which one is higher by just considering point B and the transformation that it would take B into D. That transformation would take place at a constant volume. They share the same volume. And there's an increasing pressure from B moving up to D. At constant volume, an increase in pressure would mean that the temperature is increasing. And the same for the transformation from A to C. Transformation from A to C would be a transformation at constant pressure in which volume is increased. Just as we described before, temperature would also increase from A to C. Basically, what I'm trying to say is that on the blue curve, the temperature, it represents an isothermal at a higher temperature than the red one. So temperature increases in that direction along isothermals. The further away you go from the origin, the higher the temperature of the isothermal would be. So now that we have introduced isothermals, let's consider an isothermal expansion and a few things that can be said about this. Okay, so along transformation AB, first thing to notice, there is no variation in temperature. Temperature remains constant. Of course, it's an isothermal. Now, temperature remains constant. That means that there is no variation in internal energy. The energy of the gas remains constant, but at the same time, the volume is increasing from A to B. It's an expansion. Volume is increasing, which means that the gas should be doing work. W should also be positive. So let's go back into the first law of thermodynamics. We have no variation in internal energy and a positive amount of work being done by the gas. So what we get is that from the first law of thermodynamics, this one being zero, W being positive, heat is positive, Q is positive, which means that heat is added into the system. Now, notice that heat is being added, but the temperature is not rising. Temperature remains constant. Be aware of that idea. Heat is flowing into the system. And how can that be? How can heat flow into the system without the temperature going up? Well, it's an interesting question, isn't it? Yeah, because usually we tend to think as heat as being and the heat being introduced into the system has been a condition for the temperature to rise, but this is not the case and doesn't have to be that way. The thing is that as heat is being introduced into the system system is using that thermal energy to do work in the same amount. So the temperature remains constant. Whatever heat is going into the system is doing work with that heat. So that its internal energy remains constant and there's no temperature increase. So the area under the graph will still represent the work done by the gas, although in this case, we cannot calculate that area by just multiplying. It's not a rectangular area and we are not using integrals. So this is not a type of question that would be asked, like calculate. It might be asked to estimate maybe, by maybe counting the number of squares and approximating that area by some geometrical shape that might be suited for this, like a rectangle and a triangle, things like that sort. Okay, but during an isothermal expansion, that's a key idea, that the amount of work done by the gas is the same as the heat that was introduced. Final comment, in practical terms, an isothermal expansion, it's a slow process. It requires a lot of time. We need to allow a gas to expand. Typically, when gases expand quickly, their temperature will go down. We don't want that to happen because we're creating an isothermal. So we need to allow the gas to expand without that temperature dropping. That requires time. It's in practical terms, it's a slow process. So final transformations, that's the last one, and there we will start wrapping things up. Adiabatic transformations, okay, our final stop. Transformations in which no heat is allowed to enter or exit the system. Of course, that means that Q is 0. No heat goes in or out. An adiabatic transformation requires the system to be either isolated with an insulator so that no heat flows in or out, or to be performed rapidly, in a short amount of time, so fast that heat just doesn't have enough time to go inside or outside. Two ways in which adiabatic transformations can be performed. Now, along an adiabatic curve, there's no like formal deduction of this expression. It's just one of the expressions that you will find in your data booklet, like PV to the power of 5/3. That only goes for adiabatic transformations, and for any two initial and final state of an adiabatic transformation, you get this expression like PA, A being whatever initial pressure and VA being whatever final initial volume to the power of 5/3. Well, you know the way, same thing on the outside, just that this 5/3 as a power is only related to this type of transformations, which are called adiabatic transformations. So given that the first law of thermodynamics is of course valid, and the fact that Q is 0, we have delta U plus W being 0 in any adiabatic transformation, which leads to the amount of work being just the opposite of the variation of internal energy, which leads to this conclusion. Of course, the amount of work done by the system is equal to the decrease in internal energy of the system. If the system is doing work, then its internal energy goes down. It's using its own internal energy to do that work, which makes a lot of sense for the internal energy to go down. It is the system itself using its own energy to push against those walls. So internal energy should go down, and their temperature should also go down. During an adiabatic expansion, there's a positive amount of work and temperature decreases. What you see here in the graph, it's an adiabatic transformations. They are not easily identified when they are represented on their own, because those are curves, and it's not easy to identify by just looking at a curve. Is it an isothermal? Is it an adiabatic? On this diagram, I have left the isothermals still there, so those gray curves, and the red one would represent an adiabatic transformation. It's usually steeper than the isothermals, although both are curves. It's usually steeper, but you can see that, hopefully, that when moving from the initial state A through this adiabatic expansion towards B, the landing point at B, it's at a lower temperature. It's not along the same isothermal, okay? An isothermal expansion would have followed that gray path over here, but now we're going down into a lower temperature isothermal. Okay, now, in many situations, it will be described, or be taken into what is called a cyclic process, a process that starts and ends at the same place. That's the idea of a cyclic. Let me read you a brief description. In thermodynamics, a cycle process, or a thermodynamic cycle, is defined as a sequence of thermodynamic processes that, key idea, begins and end at the same thermodynamic state. That is, begins and end at the same pressure, at the same volume, at the same temperature, and with the same amount of internal energy. Okay, makes a lot of sense. It's a periodic cycle. We're going back to the same place. Involves energy transfers in the form of heat and work between the system and its surroundings. We'll explore two of this, or two different ways in which these processes can be performed. Let's start with this one. No specific adiabatic, isobaric, isothermal, no, just a curve, just being represented. Not all curves are given names. Now, I really need you to pay attention to the fact that there's some arrows in here. So let's say that we are starting at, I don't know, let's call this point A, moving towards B through the upper side of the curve, and then going back through the lower side. That will be a key idea in here. So let's start first describing the expansion. The area under that expansion represents work, the work done during the expansion, which is positive. Delta V is positive, the gas is expanding itself. As we saw earlier, there's a positive amount of work being done during the expansion. Now, as the gas is taken back to its original state, there's work that needs to be done in order to take the gas into its original state. There's the work that needs to be done by external agents. So the work now it's negative because delta V is negative. Of course, not the area is negative, but the amount of work that area represents would be negative. Now, if you compare those two shaded areas, you can clearly identify those two areas are not the same. One is higher than the other one. Which one is higher, the positive one or the negative one? That's a key question, isn't it? Well, the difference between those two areas is the area inside the loop. And it's positive, by the way. The positive one was higher, but only because of the way the path was taken through the upper side first and then back through the lower section of the loop. So we have a total amount of work that's positive, meaning this cycle, this system is doing work on the outside. But there's no variation of internal energy after one turn through this loop because the system goes back into the same temperature, pressure, and volume. Everything's the same after one turn around this loop. So we have a positive amount of work, no variation of internal energy. That leads into Q being positive. And do you remember what was a situation in which work was positive and Q was also positive? That means that heat is flowing into the system while the system is doing work. Heat is pumped into the system as the system is doing work. Okay, because of the way we were rotating through this loop in a clockwise way, this corresponds to what's called a heat engine. Okay, that's a machine, a device to which you provide heat, like a steam engine. You provide some heat, and then you expect that device to do work on the environment. Of course, the opposite will happen if we go in the opposite direction. Let's go quickly through this. Okay, if we now go anti-clockwise, the situation will be, well, just reversed, of course. Now, during the expansion, the positive amount of work will be the smaller one, and the negative during the compression will be higher, just because of the way this cycle is being covered. Like we first go through the lower part of the cycle and then we go, and remember that it doesn't really matter which type of cycle you're dealing with, whether it's an isothermal combined with an adiabatic or an isobaric with an isovolumetric, the shape is not relevant. Okay, I just created any random shape for this graphs. Okay, the only relevant factor is whether we are going clockwise or anti-clockwise. Okay, now the situation has, of course, flipped. With the area is higher for the negative one during the compression. Higher area during the compression, smaller area during the compression. The area of the loop, the area inside the loop, will still represent the total amount of work, the difference between the positive and the negative part, but now it's negative. So you have a negative amount of work, still with no variation in internal energy, which leads to Q being negative. That means work is being done on the system as heat is being extracted from the system, which are called refrigeration cycles. And this is what your refrigerator does. In case you do have one, that's what it's doing. It's using electrical work to pump heat out of the refrigerator. One of the cycles, and this is our final slide. One of the cycles has like a special name because of its relevance. It's called the Carnot cycle. It's the only one that gets a name out of the many cycles that were created and they exist and are based the working principles of different engines. This is the one that needs to be studied within the AB, the Carnot cycle. Okay, it's an idealized reversible thermodynamic cycle comprising of two isothermal and two adiabatic processes. It's a cycle, it's a loop. It's like the one we were just using, just that it looks different because of those four segments being, two isothermals and two adiabatics, and they're all curves. There are no straight edges in this four kind of sided figure. They're all curves. So how can we identify the starting point? Which one are the adiabatics? Which one are the isothermal? That's a very interesting question. It's not easily answered. And one way that I've realized is if you take the highest point, the steeper one, this one will be the adiabatic. They're always steeper than the isothermal. And from A to B, we have the isothermal, The steeper one is the adiabatic, the other one is the isothermal. So from A to B, we have an isothermal expansion, no change in temperature. That temperature will be the highest temperature, which is represented as TH, H for hot. There's no variation in internal energy because temperature is not changing. There's a positive amount of work being done since it is an expansion, and heat is inserted into the system. During BC, it's an adiabatic expansion. No heat is being exchanged with the surroundings in here. Q equals 0. Still, there's a positive amount of work because we're still expanding the gas from B to C. And since there's a decrease in temperature, along the adiabatic expansion, there's a negative variation in internal energy. I'll go quicker because it's kind of the opposite as we reverse the process from C to D and then all the way up to starting point at A. We have an isothermal compression at along CD at a temperature that is represented as TC by the cold temperature with which the system exchanges heat. No variation in internal energy, negative amount of work, and heat is extracted from the system. Q is negative. Finally, dA similar to BC, an adiabatic compression. This one, volume is decreasing adiabatically. Work is negative, the temperature goes up now. And final comment is that along the formulas that are given to you in your data booklet, you will find this expression for the efficiency of the Carnot cycle. It's only defined in terms of the temperatures, the cold temperature and the higher temperature with which the system exchanges heat. And this was it. There was a lot of theory to cover. Hopefully you're still with me and I have managed to describe things in a way that was clear for you. Now, let's hit with those Q&A because there are probably many questions that are still floating around. If you haven't done so already, please scan this QR code and that will take you straight into the a Google form to provide us with some feedback. Will be highly appreciated. Now, Gordon, how
Yep.
are we doing with the Q&A?
Can you see the Q&A? Or
Wait, wait.
it's okay. I can read the question.
Now I can. Yes, I can.
There's a question. He's asked it twice. Hashem, I've been thinking about it, but I was going to leave it to Alejandro. He's asked about a full cycle and no change in entropy for the cycle.
Now I can see the question. Isn't a full cycle provides no change in entropy since the gas returns? Oh, excellent question. We haven't discussed entropy. And the answer, no, the entropy is changing because the entropy is related to exchange of heat. You might know from the equation that whenever heat is being exchanged, there is an entropy change. Let me take you back, Hashim, to any of those two situations, cyclic situations. Like take the bottom one, for example, that's representing a refrigeration cycle. Within this cycle, heat is being pumped out of the system, which means that there's a negative. Q is represented by a negative value, which means that the entropy of the system decreases. That takes place within any refrigerator. Inside the refrigerator, entropy decreases at the expense of a higher increase in entropy in the surrounding environment. Entropy does change. Yes. Any other questions that I should be reading out, Gordon?
We're getting lots of requests for talk about entropy and the entropy equations, which you could probably. Do you feel comfortable talking about those for just a couple of minutes?
Yeah, of course, sure. Yeah, it was doubt that we had when prepared for this presentation, what the time constraints were. There's a lot of theory to cover. We could, of course, discuss anything entropy related. It was not originally planned as part of the presentation. Yeah, are there any questions that we should be trying to answer?
Well, maybe you could just talk quickly about the two entropy equations, the delta uh, was it Q over T?
Yeah,
ES
of
equals
course.
Q over T, and then the microstates one.
Yeah. Oh, let me. Yeah. I just need a few seconds. I would really like to bring those equations forward. Okay. Okay. One of the equations that you'll find is the one that defines entropy in K in terms of Gordon. I'm sure you help me out if I'm missing something. KB Boltzmann's constant times the. I'm not sure if it's written in terms of natural logarithm or just log. I think it's natural
I think
logarithm.
it's natural logarithm of, and they've got a
What's the symbol they use? They use
omega.
this
That's
omega,
it.
right?
Yeah, that's it.
Yeah. I'm sorry, I don't have my phone here. Okay. This is a new equation within the syllabus. If you've been practicing with past papers, you haven't ever used this equation. We're not sure. I mean, it's a discussion that we're having how this might be evaluated. Just for the record, this equation will allow you to calculate the entropy of a system given the number of available microstates. Number of available microstates. Now, I will not step much further on what that means, but just to give you an idea, it corresponds to the the number of possibilities that microscopically exist for a system that are compatible with the same macroscopical variables. Let me expand that idea. Any system that's defined in terms of, let's say, volume, pressure, and temperature, we might observe that a volume remains constant, a pressure remains constant, and the temperature might remain constant as well. But at a microscopic level, things are moving, things are changing. The system is evolving, it's changing from one microstate into a different microstate, all of them with the same volume, pressure, and temperature. Having the same macroscopical variables, pressure, volume, temperature, might be compatible with hundreds, millions, trillions of microstates. This omega is representing that number of microstates of a system. It is assumed to be 1 at absolute zero, situation that leads into zero entropy, number of microstates. But we haven't seen any questions related to this, the usage of this equation within the AB. So
Yeah,
there's not,
I'll
Gordon, yes.
just I'll just add in. Yeah, this is really new, and we do have a few questions in the RV question bank that do make use of this equation. So you might want to play around with those ones. Those were sort of the best ways that we could think of asking questions about this. I will say this omega value for number of microstates in trying to make questions, that number of microstates number has to be absolutely enormous to get an S value that kind of makes sense. Because, when we get changes in entropy of like 120 or something like that when we use the other equation, if you solve backwards for an entropy of 120 and you solve that to try and find what omega is, you get something like 10 to the power of 90 or something like that. So we're talking vast, unimaginable number of microstates. Whereas if you think of a mole of gas with 10 to the 23 particles, and then we're talking about all the different ways those particles could be arranged and moving, that's where the enormous numbers come from. So I think any question you get on this is going to be quite simple, and you just need to be able to work with it.
Yeah, that's what we think. Yeah, we all agree on that. That number that Gordon was just describing in terms of that number counts the number the number of microstate, like all the possibilities that a system that is formed in the order of 10 to the power of 23 particles. Think of how many combinations of speeds and positions and things that a system might have. It's enormous. It's way over any calculator can handle. So we expect that any question related to the usage of this equation might either just give you the omega value so that you can maybe calculate something. Now, there's another equation related to entropy, which is a second related to the second law of thermodynamics. That hopefully I'm not messing things up. I don't have a copy of the formula booklet with me, but Gordon, you help me out. I think it's written as delta Q over T.
Yeah, that's correct. Yeah.
Okay. So this is not an equation that will allow you to calculate the entropy, but variations in entropy. That's why the delta S. On the previous equation, there was an actual S. For this one, we can only calculate the variation of entropy on a system by dividing the amount of heat flowing in or out. Remember that this delta Q can be either positive or negative, leading into a positive variation or negative variation in entropy divided by the temperature. Now, that temperature is assumed to be the temperature with which the system is exchanging heat. Like when a system, like a refrigerator, exchanges heat with a surrounding, that temperature is the temperature of the surrounding, the heat source, the outside object with which the system is exchanging heat with, receiving heat from, or to which heat is being extracted to. Those are the only two equations that you will find describing things, entropy related stuff.
Yeah, that second equation is kind of useful. Do you want to quickly run through like the
Oh,
idea of this
wait, we
one?
have a question by Adam Fati. What is the unit I meant of microstate? No unit, it's a number. It's a number, like actual number, like
Yeah.
integer number. It should be an integer number, like the number of things, a countable thing, no units for that omega. Sorry, Gordon, I interrupted you. I think there was another
Yeah.
question.
I'm just wondering, so for that second equation, like if we could just do the example of like two objects that have different temperatures transferring heat, and we can quickly prove that there are changes in entropy, that there's a net increase in entropy of the universe. Do you know what I mean?
Yes, of course. Let me see if
Yeah.
I have some. I wonder if I can create an empty slide as the presentation is going. I'm not sure. Can I? Oh, this is a final one. I'm not sure if I can create an. I'll just go to a random place. Oh, sorry about this. I know I created a lot of trouble. This was not originally planned. So let's do it right here. Could you repeat, Gordon, the example? The one, what, two
Okay, so
objects?
let's say, so maybe we put two blocks next to each other
Yeah.
and put one of them at one of them's at 250 Kelvin and another one's at 300 Kelvin.
Okay.
And so we're going to have a transfer of heat from the warm block to the cold block. So let's say we have 50 joules moving. So Q is 50.
So we have Q going from the quarter. Yes.
Yeah. And let's say that's 50 joules.
So let's say that this system is named 1 and this is
Yeah.
2. We have a delta S for 1 and we will have variation. Is this what where you're headed, Gordon?
Yeah, exactly.
Okay, so what is delta S for 1?
So that's going to be
You
so
said
one.
50.
You've got this, right? You know what to do? Sorry, I'll
I
let you
think
go.
so. Yeah.
Yep.
Just let me know if I'm stepping away from what you originally planned. You said 50 joules of heat flowing from 2 into 1. So 1 is receiving 50 joules, whereas for 2, the 50 joules are being extracted from. So we have negative. Oh, by the way, if you're lost, what we are using is this equation, delta S equals delta Q, the amount of heat flowing in or out, divided T. Now, what are the temperatures in here? By the way, we are also assuming that as heat is flowing from one object into the other one, their temperatures are not changing. Like the objects are large enough for the temperatures not to vary. Think of, I don't know, the Atlantic Ocean at the atmosphere. Heat can be exchanged and the temperature of the objects will not vary significantly during this process. Now, at this point, realize that one of them will lead into a negative value, the other one will lead into a positive value. What is the temperature at which T1 is? We have 215 here. And we have 300 in here. So let's do this. If you have a calculator with you, you can just help me out. 50 over 250, we have 0.2. That's the increase in entropy for 1 joules over Kelvin. Whereas for we have negative 0.167 or something like that. But at this point, you can hopefully see that the increase in temperature in one part is not the same as the decrease in temperature of the other part. There's a total increase in temperature. So the universe, the system in itself has increased its temperature only because heat was exchanged. And
System is, yeah,
I think this
system.
will,
So
yes.
yeah, so overall the system has increased its entropy. And this is always going to be the case, right? Because if you look at those fractions, I'm just adding to what Alejandro has said. Yeah. If you look at those fractions, the negative fraction, because of the bigger denominator, is always going to be smaller in magnitude than the positive fraction. And so the net will always be positive because the heat flows from the higher T to the lower T.
So this will always be positive. Omar, Gordon, there's an Omar shout out that seems to be asking questions. I don't know. But please answer me before the session is over. I do not know what the question is. Maybe
Yeah,
Omar's
Omar,
shout out.
many questions.
Yeah.
I've been working hard to keep up. It was very similar on the other night. I believe it's the same person. Um, Yeah, so I'm going to still keep chipping away at these. Uh,
Okay.
Answering Adam, sorry, quickly. Yeah, it's the sum, but one of them is negative, so you end up subtracting the negative value, right?
Yeah.
Uh, Tanishi's asking, will it be recorded onto revision later? Yeah, we will post recordings all of this, so you can go back, but it might not be till Monday, actually, when people are back at work. The entropy value itself is always positive. Change in entropy can be positive or negative. But for any process, net change in entropy, total change of entropy, considering everything, will always go up or be zero. Um, Omar's asking for the PV to the, is it 5/2 equals constant equation, and whether we could prove this, how that turns into a relationship for,
This one?
yeah, I believe there's a related, that PV to the 5/3 is constant. And then he was asking for a derivation. I can't, it's answered. Hang on, I can see this.
Ah, yes. Okay. I know what this
Does
is.
that
I
also
think
PT
so.
to the negative 2/3 is constant, he's saying. Is that true?
Yeah. Yeah, that's something that just needs to be the gas law needs to be inserted in here and work with the algebra in here. Which one? There are like many derivations that one can get by inserting the ideal gas laws equation in here. Which one is the one the Omar wants? The PT to the negative. Okay, so PT that means we need to get rid of that V. That's all that it means. So from the ideal gas equation. Specifically for your question, Omar, PV equals, I don't know, nRT. So let's solve it for V, which leads to V equals nRT divided P. And that needs to be affected by a 5/3 power. So let's bring this equation forward and let's cancel all the constants out. So yeah, PA times, instead of BA, we can just write the number of moles. This will get simplified, same as a constant. TA divided PA. This is the volume. This is volume A. Still need to be affected by that 5/3. Same thing on the right side. We will have PV times volume B. That'll be number of moles times R times TB divided PB. Hopefully I'm not messing things up, to the power of 5/3. Let's get rid of all the constants. R like this. And the pressures, we can subtract exponents, right? Because we have, just give me a second. We have PA to the power of 1 divided PA by the power of 5/3. It's 1 minus 5/3. That's negative 1/3, negative 2/3. So we will have PA to the negative 2/3 times TA. This is for those of you watching, this is just an algebraic consequence of the usage of the adiabatic law and the ideal gas. So same thing on the right side, PB to the power of negative 2/3 and T to the power of 5/3. Now, which one you wanted? You wanted the one with P T to the minus something. Okay. In order to have P, we need to like take all the left-hand side and all the right-hand side so that the exponents on the P get cancelled. So we need to do like to the negative 3/2 so that we just have P, because that's specifically the one you wanted, Omar. Negative 3/2 on both sides. So that's where we get PA. What is it? TA2. I get negative 5/2. I think so. I'm solving this as I move along, so I'm not entirely sure. Hopefully, I did things right. P, B, and then T 5/3 to no to negative halves, negative 5/2, I believe. This will be the derivation. Okay, Omar, hopefully that's what you asked for. Question, Lucia, you answered this question. Is entropy always positive? Is entropy for Carnot cycles zero? No, it's not. During the transformation, heat is being exchanged. The entropy is not zero. Responding for Noah, I'm not sure if you have answered this question, Gordon. Responding for
I'm writing Noah's answer now. Yeah.
okay, okay.
Or maybe I'll give it verbally. People are back and forth about what the grade boundaries are going to be. And the answer is my
Oh,
guess is higher because you have more time than previous grades have had. But we don't know. And actually, do the grade bound do our opinions on the grade boundaries affect how much you're going to prepare for this exam? No. I know you would like us to say, don't worry, the grade boundaries are going to be lower. But I will say the grade boundaries have been outrageously low for the past, I don't know how many years, I think. And so my opinion is they're going to be higher. Alejandro, do you have a guess? We're just guessing, folks.
no, yeah, just guessing. I mean, guessing. I'm not even sure how they work. Being an examiner, I don't know how they work. I'm not even sure if they have been decided yet or they decided
No, to
afterwards.
decide boundaries, they get papers. I do know how this process works. They get the papers back, and then they'll sort of say, I think the boundary between a 5 and a 6 is here, and then they'll get a selection of papers that sort of fall on that grade. And they'll start looking at those papers and actually just go, is this paper a 5 or a 6? Is this paper a 5 or a 6? And then they move that boundary to slot it in. But it's a bit of a judgment call. They have descriptions, I think, about what a 5 should look like and what a 6 should look like. Seems a bit odd that in physics it's done that way, but I believe that's the process for all subjects. I know it's definitely done that way in a certain humanities subject. So it really is just a case of them trying to decide where it fits. I think there might be an element of looking at not so much a curve, but the percentage of papers that will fall into each category. But ultimately, it's supposed to be an objective. Where is the cutoff between people knowing it really well and not so well? If that is the sort of definite, we have a better definition of the difference between a 5 and a 6. All right. We're really, I think this meeting automatically ends in a minute. So we're going to have to say goodbye. And thank
We
you.
got a lot of questions.
One more, tons of questions today. I'm at 98 answered on the Q&A.
98 questions you
Yeah.
answered. Oh, Gordon.
Here again is the link to the feedback doc. We'd really appreciate feedback. Thanks to everyone for coming. Um,
Yeah, thank you very much.
um, Next week is we got 2 more sessions. I believe one is on Tuesday. Time zone might not work so well, but then next Saturday, very similar time for this, we have one as well. Okay, so thanks to everyone for coming. Someone's asking for last session's slides again, so I'm going to try and dig those up. All very busy. Big thank you to Alejandro for his time as well for this, and for so many students for attending.
Oh, thank you very much.
I'm trying to get the circuits one posted. Here's the circuits link coming in from last week's presentation. All right. Bye, Omar. Thanks for attending both
Bye,
sessions.
Omar. Bye, Omar. Bye,
Bye.
multiple
Okay,
stuff.
students, we are pretty much done here. How do we?